Sir, I guess we can start. Over to you, sir.
Okay, Dr. Dipti. So let's start again and right from the point where we left. So we were talking about ANOVA and F-test. So I think the F-test is clear. So we come to coefficient. So these are the parameters. So how do we report this equation? Is like this. How do we report the equation? Let me just see. Yeah, so this is the reporting of the equation. So our independent variable was time. So y is equal to beta 0 plus beta 1 x. Here y was time and x was a diameter. So our equation is time is equal to 5.845, which was the value for the constant. And the beta parameters value was minus 0.142 diameter. And we need to report these two values like t value and the p value. So these two values are very important. How this t value is calculated is, you can see here the beta coefficient divided by standard error. So these three are related to each other. So standard error comes as a denominator and numerator is beta coefficient. So these three are related variable. 7.407 is the t, and beta coefficient was 0.142. Of course, unstandardized beta coefficient, and 0.109 divided by 0.019 is the standard error. So we can go back to the basic question. Before we go to the hypothesis testing, we go back to the basic questions like, first, let's tackle this question. Which one should we consider, unstandardized or standardized? Your response.
So, unstandardized.
Unstandardized, the right answer. Very good, congratulations. But the next question follows is that, what is the difference between unstandardized and standardized? And why we are not using a standardized?
Standardized talk about only beta 1.
Mm-hmm. Oh, it doesn't have constant. Okay.
Huh.
Yeah, very sharp answer.
Doesn't talks about the intercept actually.
It doesn't talk about intercept. It has only slope.
The slope.
So it's not usable. Very good. That's a very intelligent answer. Okay, anybody else? All right. So generally what happens is that the standardized form of the data, the standardized coefficients are actually calculated on the basis of a standardized form of the data. So what is it called, a standardized form of the data? The standardized form of the data is the Z transformation of the data. So we all know Z value. There are many ways data is transformed in research when we are dealing with them. If the data confronts some problem, like we convert them into log, we also convert them into Z score, we convert them into some other transformation that we do, depending upon what kind of model, what kind of data we have. So when we convert the data into Z score, on the basis of Z score, if you calculate the regression, this is the beta you will get, 0.700 you will get after the Z conversion of your data. So that's called a standardized coefficient. Now the limitation of the standardized coefficient is that it will not give you the right kind of prediction, right? And that's why we do not use standardized coefficient. The advantage of a standardized calculation is that it gives you the robust calculation without any bias, because when you convert the data into Z score, then the normality of distribution is ensured, because Z transformation of data is based on the properties that the data will have the mean, which is equal to 0. The sum total of the mean is equal to 0, and the standard deviation is always going to be 1. So if you calculate the standard deviation of your original data and calculate the standard deviation of the Z transformed data, the standard deviation may be very high or low in the original, but in Z transformed formation, it will always be equal to 1. So you control for the variability of the data and then calculate the regression, which is a very good way of calculating the regression. But the only limitation is that you do not actually get the right kind of prediction. And that's why one of the purpose of the regression is prediction. And so we do not use the standardized data. That's the difference between the two. I'll give you some good insight into it. Let's go to analyze. Let's say we go to descriptive. We go to descriptive statistics, and then I said, okay, for time and for diameter, give me some save standardized value as variable. So give me a standardized value of these two variables, like time and diameter, which is used in the regression. And we'll say, okay, the moment we say, okay, in the original data set, if you go to look at your original data set, there are two columns which is already added. You can see here jet time and jet diameter. So these are the jet transformation of the data. And if you look at these two jet transformation of data and calculate the project the histogram of the two, you will see it a perfect normal distribution that will come. So vis-a-vis, if you want to try and compare what is the histogram that you're going to get between time and diameter, the original data, and what is the histogram you're going to get between the jet time and jet diameter. If you compare these two histograms, you will find that this histogram may be lopsided, but this histogram will not be lopsided. It's going to be a perfect normal distribution. So that's the beauty of jet transformation. And if you actually calculate regression now, go to linear and then say, okay, fine. So I'm going to give me the regression between the two variables which are transformed variable, right? So what should be the beta coefficient of this equation, of this regression? It should be 0.7, right? Because unstandardized beta coefficient was 0.7. So you just check whether it is coming 0.7 or not. 0.7, right? You see here, 0.7. You can see that. So this standard coefficient and unstandard coefficients are the same, 0.7, 0.7. So this means that the standardized coefficients are calculated on the basis of a standardized score, and standardized scores are jet transformation of the data, right? So, and therefore in regression, in practicality, we do not use standardized, we use unstandardized. Is this answer clear to all of you? Okay, so I have to go back to this table. So is this point clear to all of you?
Yes, sir.
Any question on that? All right. So we go back to this we have already seen. So here, null hypothesis. So, you know, why do we need to actually test hypothesis or look at that? If we go to the table again, we find that here the diameter has beta coefficient 3.457 and the t value 7.407 and the corresponding p value is 0.000, right? So if your p value is less than 5, the rule of the thumb is that you reject the null hypothesis. So what is the null hypothesis here? The null hypothesis is that the beta is equal to 0. That is your null hypothesis. So when you reject the null hypothesis, you accept the alternative that beta is not equal to 0. This means that your beta coefficient calculated is significant. Now, what does it mean when we say that beta coefficient is significant? And what does it mean when we say that beta coefficient is not significant? Now, when we say beta coefficient is not significant, this means we are accepting the hypothesis that beta coefficient is as good as 0. Means it has no other value than 0. This means 3.457 is not, it's just the face value you can see here, but it's almost like 0. It has no validity if you accept the hypothesis that beta coefficient is equal to 0. So just imagine, suppose you have to calculate the average height of the people residing in Indore. What is the average height of people in Indore? Suppose you want to do that. So the entire population of Indore is population And then you're going to divide Indore into different, age group, or maybe, administrative zone, and you do the stratified sampling or best of the sampling that you do. And then on the base of 2,000 people that you have asked, what is your age, height, and then you calculated the average of these 2,000 people and said that, okay, this is the average height, 5.6 is the average, or 5.8 is the average for Indore. Is it correct to say this, that average height of Indore will be 5.8 if your sample says the average height is 5.8? Is it correct to say this? The question is that it is based on a particular sample. But if I change my sample, listen to this very carefully. If I change my sample, if I take another set of 2,000 people, will the average be the same in the second set of sample? Maybe, may not be. We may not get 5.8. If I change my sample again in third sample, will I get again 5.8? No, there is very, what is the probability that I will get 5.8? Now, question is that if I take any sample from this population randomly, and if I get 5.8 exactly, what will be the probability that I will get? If the probability is more than 5%, that I will not get the same result. This means in the first sample, if I get 5.8, in the second sample, if I get 6 or something like that. So 5.8 has no validity. Actually, it is almost like 0. I cannot use this 5.8 because I'm not sure whether if I draw the sample again, I will get the same 5.8. And therefore, the question of validity is very important. And your result, your test statistic is valid when you find that the probability of getting the same result, if you repeat the sample or if you change the sample, is as high as at least 95%. So that is what the P stands for. So if P stands for the fact that if you change the sample from the same population, what is the probability that you are going to get a different result? And if that probability is less than 5%, you say, oh, okay, I'm done. Fine. So 5% error, but I'm fine. 95% accuracy is there. And this is called the validity. Unless this validity of the result, and validity is about what? Validity is about the fact that you are able to predict the population, because the purpose of research is to predict the population. Purpose of research is not to draw the sample and do the research. Sample is drawn for the fact that you really want to talk about the population. That's why you take the sample. If you do not want to talk about the population, the research has no meaning, right? Because research is not about sample. Sample is just an evidence that you collect from the population. And there used to be something called the Monte Carlo simulation. The Monte Carlo simulation was about n number of sampling that you draw from the same population. So if you keep on drawing different set of people from Indore city, n number of times, thousands, millions number of times, and then you find the average of averages of all the sampling, this will give you the right picture of the average height of people in Indore, right? But we do not have time, you do not have money to do the to draw the n number of sampling. So we are basing our result on one single sampling, right? So we do the sampling in a most possible plausible way, best possible way, and then we are trying to draw. But no, this kind of inferential statistics has actually helped us in doing this. So this is why it is called the inferential hypothesis. Inferential hypothesis about the fact that how do you infer the information about population from a sample that you have drawn from the population. So p-value. So if p-value is less than 5%, that means the probability is less than 5% that if you change the population, the sample, you will not get the same result. And that's why the 5% is the rule of the thumb, because in social science, 5% error is fine, right? So that's why the value of significance here in the last column, you can see 0.000. That means there is negligible probability that if you change the sample, you will get a different beta, right? So this is the meaning of 0.000. P is equal to 0.000. If P would have been, let's say, 0.03, what would have been the interpretation? The interpretation would have been there is 3% probability that if you change the sample, you will not get the same beta. Is it acceptable to you? I'll say, oh yeah, it is acceptable. 3% is fine with me. So up to 5% is fine. So 0.05. That is why 95% significance, right? So therefore, this beta is valid. So let's go back to this one slide to look at the hypothesis testing. So your null hypothesis beta is equal to 0. That means beta has no validity. You cannot trust this beta. If you change the sample, you may get a different beta, right? So this result is invalid. Alternative is beta is not equal to 0. Not equal to 0 means, yes, it is significant. It is different from 0. When you reject the null hypothesis, accept the alternative, your beta is called significant. That means, what does this word mean? Significant means in statistics. The word significant means in statistics that it is statistically significant. So statistically significant means the result is valid. Even if you change the sample, you will get the same result. It will not give you this different result, right? And that's why your result is valid for the population. So your test statistic is an example or is an evidence, valid evidence for the parameter that you're trying to calculate. And that's how it works. So if you look at the first graph, where from this hypothesis comes? What is the origin of this hypothesis? So in regression, imagine the days when the regression was not invented and there was no regression, suppose, and you had to predict something. So today we have the regression, so we run the regression and predict. But statisticians, how they were predicting when the regression was not there? So they were using something called the mean model. It's called the average model, the mean model. You can see here. The mean model is about the fact that the regression line is straight, right, parallel to x-axis. This means that the beta coefficient is equal to 0, right? So mean model means the regression line is straight. This also means that the x is a stochastic variable. That means x is changing. And because of the fact that the x is changing, the y is also changing. That's what the regression is all about. But here in mean model, x is a stochastic, but the y value is always going back to the mean. So what is your best prediction in the absence of any regression? The best prediction is that whatever is the value of x, the y will go back to its mean value. So that means the average value of the y is my best prediction. So that is what the mean model is all about. But question here is that, is your regression doing anything different from the mean model? If your regression is actually giving you the same result as the mean model, assuming that beta is equal to 0, this means your regression has no value. It has not added any value to your, it's a wastage of time. And therefore you can see here in the second graph, if your model, regression model, here the beta is not equal to 0. This means unless the beta is not equal to 0 or statistically significant, regression has no value because it is as good as mean model, right? And that's why it is very important that we go for the t-test. But the catch here is that in a single variable regression, which has got a simple regression in which we have got only one independent variable, just one single independent variable, the t-test of the beta and the f-test for the whole regression are the same. They are giving us the same result. They are not different. So in simple regression model, if you have f significant, this means your beta is also going to come significant. You don't need to run the t-test separately, right? So you can see this one to give you the idea, right? So here the value of f in a single simple regression is going to be equal to t square. So there is no difference between t-test and the f-test. So here in your regression, the value of t is 7.407 and value of f is 54.8636. In the calculation, you can see that. And if you multiply this t with t, that is, if you double this, 7.407 multiplied 7.407, it will exactly give you 54.8636, the value of f. So that means t square is equal to f. And this happens only in simple regression, not in multiple regression. And remember, in simple regression, you have got only one variable, and that is why you use the R square. But if you have more than one variable, that is multiple regression, you will not use R square. There you will use adjusted R square, right? Why adjusted R square? Because the more you add on the right-hand side of your equation, the greater the chances that your y will be better explained. So even if you don't know which variable is affecting y, you just keep on adding variable on the right-hand side. You add 50 variable, of course, somewhere or the other it will affect y, right? So the explanation that will come from regression will automatically tend to increase if you keep on adding value on the right-hand side in the multiple regression, right? Oh, this is a problem in regression. This is a big problem in the regression. So whether these variables which you have added on the right-hand side are the right kind of variable or not, they're really adding to y or not, but the value of explanation coming from y will keep on increasing if you keep on adding on the right-hand side. And therefore, your R square is going to increase automatically if you add variable on the right-hand side. So R square may not be the right representation of the model fit, right? How do you measure the model fit? One of the way to measure the model fit is R square. So if R square is higher, the model is better. So that's what we call the model is a good fit. So the goodness of fit for the model will keep on enhancing if you keep on adding the variable on the right-hand side. And that's why we do not use R square. We will adjust it for degree of freedom. So the R square is actually adjusted for degree of freedom. There's a formula for that. And then adjusted R square is calculated. And this is used in multiple regression. So somebody was saying adjusted R square to be used for simple regression. And this is why I said that in simple regression, there's no need for using adjusted R square. Is the R square which is enough. But for multiple regression, you cannot use R square. You have to use adjusted R square. So we have come to this far. I'm not able to see anybody. Is there any more question here before we move forward?
No, sir. No, sir.
Sir, sir, I have a question, sir. Can you?
Yeah, sure.
Sir, I have seen in most of the research paper, they even reported in using the multiple regressions, the R square, but they have never reported the somewhere adjusted R square. They said that R square is above 0.60, the model is good fit, and
I don't know about that, but you have freedom to report both. But adjusted R square is necessary to understand the goodness of fit for the multiple regression.
So that means you are saying that if you add more variables in your model, the adjusted R square is going to change.
No, adjusted, this is not what I'm saying. If you keep on adding variable in your model, your R square will keep on increasing. And therefore it becomes a little unreliable to be used as model fit. So you have to adjust this R square against the degree of freedom that you actually, degree of freedom that changes with addition of the variable. And then that can be used as a model fit. This is what I'm saying.
R square will always be higher than the adjusted R square, sir, na?
Oh, 100%, because this is a direct correlation and it's adjusted for degree of freedom. So adjusted R square will be lower.
Okay, sir. Fair enough. Thank you, sir.
Yeah, okay. So should I proceed now? All right. So we are now coming to a slightly difficult part. So you have to be a little careful. Now look at this one. This is a very difficult word in econometrics we use. I don't know how many of you are aware about. It's called heteroskedasticity. Can you pronounce that? And do you know about it? So you're doing financial econometrics. So therefore, it's very important that you know about autocorrelation, heteroskedasticity, and other issues related to the error distribution. So there is a lot of treatment that you have to do for the error term. And one of the things in regression we use is called, one assumption, which is known as assumption of equal variance in the error distribution. So what it says is that your error part, that is E part, now we have focused so far on the regression part. So now we are focusing a little bit on the E part. So it is saying that the error part, it has a certain distribution. And if that distribution is not equal, or the variance in that distribution is not similar or constant, it is going to affect your beta value, or it will inflate your beta value. And it will be, your result will be unreliable. And therefore, in order to achieve a great deal of reliability in your calculations, your regression, you must diagnose for what is happening to the error. One of the diagnoses that you can do is that is called the assumption of homoskedasticity. Homoskedasticity means that the distribution of variance, the distribution of error and the variance of that distribution is equal, or is same, or is constant over the distribution of your dependent variable, or your the changing variable that you have taken into account. So let's understand the error first. So error is the difference between, let's say, the y minus the y estimated. So you have a y, which is the actual y, and when you estimate the regression equation, the difference between the actual and the estimated is the error. So quite often you calculate the regression, and you have the different values for y, which you calculate on the basis of given value of x. And then if you try and find out the difference between the actual y and the predicted y from the regression, you will find that there is some kind of difference that will emerge out of the two. The difference is called the error. And if there is no error involved and 100% explanation coming from the independent variable, then the difference will be 0. Right? So that's what error is all about. So error is y minus y estimated. Now in regression, the basis of regression is called the OLS, is called the ordinary least square method. And if you look at the name, ordinary least square, a square means doubling. So something is doubled, and the minimum value of that double value is trying to be achieved by the regression equation. That's what the purpose of whole inner mechanism of OLS is. So what is that is doubled? It is the error that is doubled, actually. So if you have the error concept like actual minus estimated, then if you sum total the error, sigma error, it is going to be sigma y minus y estimated. That is the sum total of the error. And generally, if you look at the mathematical properties of mean, arithmetic mean, then if you deviate a series with its actual arithmetic mean, then the sum total of the mean is always going to be equal to 0. That's the basic fundamental property of arithmetic mean. And if you look at the regression line actually passes through the mean. All x on y or y on x, both the regression lines, they cross each other and they process through the mean. And therefore, if you try and find out y minus y estimated and add them together, you will always get equal to 0. The total will be always equal to 0. Y minus y mean, y estimated from regression, and then you find out the sum total, it will always be equal to 0. And therefore, it is not the sum total of mean that is to be minimized, because it is already minimized. It is already 0. Sum total is already 0. And therefore, what we do is that we actually square up the error term. So it is sigma error square. That means sigma y minus y estimated square, that is to be minimized. In the ordinary least square method, the regression that you use, what is minimized is the sigma y minus y mean square. And that's why it is called ordinary least square. So that's why it is called OLS method. Now, these two equations are for those who understands mathematics, but if you don't understand mathematics, is fine. You can ignore this. So the process, mathematical formulation of the regression is you minimize the sigma e square. So what you do is that you minimize sigma e square with respect to beta 0, that is one parameter, and make it equal to 0 for the first conditions of minimization. And then again, you minimize the error square with respect to the parameter, another parameter, which is beta 1, and then make it equal to 0, which is the first condition of minimization. So minimization has got two conditions. One is you first derivative has to be equal to 0 and the second derivative has to be greater than 0. So this is the first derivative. And if you calculate this, if you go for the mathematical calculations for this equation, derive it, you will get the first normal equation. If you expand upon this, you will get the second normal equation. The two normal equations will give you the solutions for regression. And this is how you calculate the value of alpha and beta. So these are the mathematical basis for OLS. So I've just give you the idea about error and what is the mathematical basis for. I don't know how many of you have understood this, but if you have interest, you can go to the book by any econometric book, and you can understand that. From my side, the recommendation would be Damodar Gujarati. So that's the most famous book in econometrics, and it's one of the easiest book ever written for the students and for the beginners. So you can go to Gujarati econometrics and understand that. So let's come back to error again. So error is equal to y minus y estimated. So y estimated is the regression equation that we have estimated, beta 0 minus beta 1 x. That is the regression equation we have estimated. So here in our case, the y is time and the x is diameter, let's say. And if you want to calculate the error, we have to calculate error like time minus 5.845, which was the value for beta 0 in our calculation, plus 0.142, which was the beta coefficient for diameter. And this is how we have to calculate error, like time minus 5.845 minus, because there is a minus before the bracket, so this plus becomes minus. So minus 0.142 diameter. So that's how. So I'm just going to note down this equation because I'll have to feed this equation in. So let me just give me a second so that I can note it down. So okay, so I have already with me. So I'm going back to now the data. Before I go to the data, anything that you want to ask on this? No response means either it's difficult to understand or you have understood everything. Anyway, I'm not able to see many of the participants, otherwise I would have asked them directly the question.
We can assume, sir, most of the participants have understand the concept.
Understood, yeah. Okay, good, good.
Right.
Yeah, that's a better way to look at it. Okay, so here I'm coming to this table. So I'm going to, let's say, analyze. I'm going to regression. I'm going to linear. And I'm going to reset because we're dealing with the data, not original data, not the, diameter. So this is the data for regression. So we go to save button. So here you can see here residuals. Residuals means error, and I'm saying it is give me unstandardized error. So there are standardized error and unstandardized. The difference between standardized error and unstandardized error you understand so well, because standardized error will be calculated on the basis of regression, which has used Z-score, right? So we are not using this error distribution. We are going to go for unstandardized error, and we say continue, and we say okay. So it will give another calculation of the whole thing because I have not de-checked that. So it has given us the residual. Now this is the residual. This is the error distribution of my regression. This is the error distribution of my regression. Now, what I'm going to do is that I'm also going to give you a glimpse of how the error is calculated. So we go to transform, and then we go to compute variable. So here we are going to compute error manually. So this is the error calculations, which has been done by the computer. But here we are going to calculate the error manually. So what is the name of the target variable? We'll say, okay, I would like to call it error. And then what is the numeric expressions that you are going to use? I'll say, okay, the calculation is going to be like this, time, and then we say time minus, then we'll say 5 point, where is the point? Let me say 5.845, 845. So I'm feeding the values. And then again minus, because I have already shown you this, 0.142 diameter. So we have to take this multiplication, and where is the diameter? So I'm carrying the diameter over here. So you can see what is the argument I have created over here for the calculation. I said that, okay, the name of the new variable will be error. And how this numerical expression going to be calculated is, it has to be time, that is y, minus beta 0, 5.845, minus beta 1, 0.142 diameter. So give me this. So this is the error that we have discussed. This is called error. So we'll say okay. And then we go to the data set. And here you will see that the error, there's a new variable which is calculated error. So this is the calculation manually we have done. And this is the calculation which is, it looks like a different figure we have got. So let me just see what is the difference. Oh, is it so? It's a very different figure we have got. It shouldn't be a different figure. Let me go back again and calculate. Did I take the right values? Was it 5 or was it this one? This was the original one. Okay, so this is not 5. So the equation is time minus 3.457. Then again it will be minus 0.467 diameter. So I took the wrong figure actually. So let me calculate again.
Or should we take the constant value also, sir, there?
Yeah, so I have taken the constant. Constant is 3.457. So yeah, so there is a constant value 3.47. You can see here. This is that
is the coefficient of.
Yes. So that's the mistake I have done.
Yeah, it should be minus 1.955.
You're right. Time is equal to, it has to be. So if we do the minus, time minus, so it will become plus. So 1.955, and then it will be minus 3.457 diameter, right? So this is what it is. Okay. Thank you so much for pointing it out. So it was my mistake. So we go to transform, we go to compute, time minus. So it will not be minus, it's actually going to be a plus. 1.955, 1.955. Okay, and then it is going to be minus, and this is going to be actually 0.457 diameter. Is this okay?
Sir, there are 2 decimal points over there.
Sorry. Oh, okay. So this decimal will go, and this is going to be 3.47. Is this correct now?
Yes, sir.
Can you check again? Is this correct? Yeah, let's try. Change the existing variable. Okay. So this is a new calculation, 12.62, 12.62, right? 16.69, 16.69, 29.6, 29.6. So, this is how the error has been calculated. So are we there?
Yes.
Did you get the idea? Okay. Now what we are going to do is that we are going to go to graph and go to chart builder. So this the window which will allow you to make the graphs. So we go to, let's say, scatter dot plot, drag it here, and put the this error, unstandardized error over here, and the value of time over here, vis-a-vis time, and then we'll say okay. So what it does is it gives us this graph. So this is the error distribution in front of us, right? The distribution of error across the y variable. So as the y variable changes, this is the distribution changes. You can also check the error distribution across the stochastic x variable. So as the x variable changes, how the error changes. So you can see here. So when you look at the distribution of error vis-a-vis x, we find that it's very, very scattered. So if you try and draw a kind of line, you can see that this line is going to go in two different directions. It will go from here, it will go from here, right? So it's not very constant distribution of error. Here with the y, it is almost like going up. So that means it's a linear positive relationship of error with y. And here, the variations in error is very, very scattered, very far, uneven. So that means this data has, or this regression has the problem of heteroskedasticity. So, so this means that the reliability of the equation is not there. The reliability of this regression is not very high. It's not very good. So next is, what to do if the reliability is questionable. What to do? So most often the heteroskedasticity is a complex problem, and it cannot be solved in one way or the other, and there is no definite way that it can be addressed. So one of the ways is to look at the data and see if there is any outlier existing in the data, or there is some problem with the data normality, distribution of normality. So probably less normal the distribution of data, less normally the data is distributed, the higher the chances that you are going to get the error distribution, uneven. So in order to do this diagnostic, quite often the data is actually is transformed. So when the data is transformed into log, it actually starts behaving properly, or data is transformed into some other Z score, then it starts behaving properly. So these are some of the way, but most often researchers actually, they do ignore the problem of heteroskedasticity in their calculations or in their reporting in the equation, reporting in the paper. So for research, if you want to go ahead with this kind of error distribution is fine, but sometimes you may be asked this question that have you looked at this diagnostic? So it is always better that we check this diagnostic a prior and look into it, because this may not give your beta a very authentic positioning in the research. So on the base of this beta, if you try and predict, the predictions may not be very, very nice. And it's also not a very good fit equation, because we saw that only 49% of explanation in Y is coming from beta, and that too, the error distribution is very uneven. So this is one diagnostic that we can look at. Fine. Is that okay? Should we move forward, Dr. Deepti? Is there any question here?
Our participants are having any questions? I guess we should move forward.
Okay. So now I'm going to give you some demonstration of.
Sir, I have a question, sir. Can I say something?
Yeah, please go ahead. Go ahead.
Sir, I have a question. Sir, that means here you are saying that variance is not constant.
No, variance should be constant. Here,
Of
variance is
error
not
term.
constant. Yeah.
Constant for the error term.
Yes. The variance of the error term should be constant across the stochastic variable X and Y that you have. But here in this case, it is not. So what it demonstrates is what it demonstrate can be called heteroskedasticity problem. While the assumption of the OLS is that it should be homoskedastic.
Yes, sir. Okay.
Okay. So moving further, I'm going to also give you some demonstration of, because linear does not mean that it's only linear in parameter, but it can also be a different forms of equations that you might use. Like sometimes the quadratic is going to help you in many ways. How do you actually measure quadratic? Sometimes log can help you in many ways. When you transform the data into log, it can help you in many ways. So how do you calculate that? So I'm going to take one example and give you a demonstration of how quadratic and logarithmic transformation can help you, right? So this is what I'm going to do. So I'm going to do regression using quadratic equation and regression using logarithmic equation. Because these have huge applications in your research. So what I'm going to do is that I'm going to obtain data, a separate set of data to work with, and this time I'm going to take data from the Excel sheet. So there are many data in the Excel sheet. So I'm going to import the data from the Excel sheet. So I'm going to go to the data for exercise file, and then it's asking what data would you like to import from. And let me just see, I have already noted the data to be imported. So I'm going to import from E3 to G24. I have already seen the file and I have noted down which is from where to where the data should be imported. So in Excel file, the beauty is that you can keep the Excel file full. You have massive data, but there is provision in the SPSS that if you want some part of the data to be imported, you can do that. So you have to specify the limit from where to where you want to import your data. So this is a limit I have actually set, that in sheet number 1, which has data from A1 to I58, I don't want to import the whole data. Just give me the data which is from E3 to G24. So you should know which part you want to import. And then when I say okay, the data will appear automatically with all kinds of variable name and everything. And you can see here the data is about, just to give you the familiarity with the data. This data has got name of different forms. Pepsi, you can see here Pepsi, Coke, Polaroid, Crest, a lot of companies data. And this is the data for impression. This is one of the research that people from management, they do quite a lot. And this is the data which is taken from the secondary source of Wall Street Journal. So this data is about impression. So they actually asked the calculator the impression retained by the customer of the advertisement done by these companies. Say, for example, if the Pepsi ad is there, and if you are asked the question, can you recall, have you seen the Pepsi ad? And you say yes. And then they will say, okay, can you recall the ad? Then, you start recalling the ad. And if you're able to recall about 70-80%, that means you are more likely to be a Pepsi customer. But if you're not able to recall the ad for less than 50%, then you are less likely to be a Pepsi customer. So the researchers have the interest that this recall value of the ad, they calculate, and then they actually relate it with the sales of the product. So here you have the two kind of data. One is recall data, impression of the advertisement, and second data you have is the expenditure made by the company on advertisement. So these are the expenditure in million of rupees made by these companies on the advertisement that they have floated. And these are the data for advertisement retention by the company. Just to give you a glimpse of how the market looks like. So I'm going to, again, to make the scatter plot. And here, what I'm doing is, let me take one of the data like expression over here, and impression over here, and go to, let's say, point ID. So I have created a point labels, and I said, okay, also give me the name of the forms. Such kind of graphs are very useful if you put it in the research paper. So here you see the scatter dots have been created with the name of the company. So you can actually have very easily, you will be able to explain. Say, for example, you look at the Pepsi and you want to understand the efficacy of the advertisement by these companies, how effective these advertisements are. So you look at the Pepsi. So Pepsi is actually spending almost half the money on advertisement in comparison to McDonald's, but they are able to create impressions more than the McDonald's. So people have more recall for the Pepsi ad than the McDonald's ad. So we can easily say that the Pepsi ad is more effective, right? And then if you have to compare the competitor like Pepsi versus Coca-Cola, then you can say Pepsi is here and Coke is here. So Coke is actually spending less than Pepsi, but the difference in the amount spent, if you see between Pepsi and Coke, and the difference in the ad retention of Coke and Pepsi, we find that the Pepsi is still very powerful and is more effective in comparison to Coke, even though the Coke is actually spending less. Their retention is far less than the Pepsi. So something of this sort. If you look at the Burger King again, where it stands, the Ford is very bad because it's spending almost like equivalent to McDonald's, but their advertisement retention is far, far less in comparison to all these companies. So this means a very inefficient ad. So something of this sort. So there are two questions here. As a manager, you may have to, manager can be asked. One is, if I have to decide the budget for the next year on advertisement, how much should I spend on advertisement? That's number one question. And second question would be, does it really make sense to spend money on advertisement? So if these two questions are to be answered, then we can resort to regression and try and answer these two questions. The first question is, does it make sense to spend money on advertisement? This means we have to go for linear regression. And linear regression can give you the idea that if the beta coefficient of this linear regression, wherein we are taking impression as a function of expenditure, presuming that as expenditure changes, the impression will change. And if this regression equation gives you a beta coefficient which is positive, this means that if expenditure increases, the impression increases. It makes sense for a company to spend money on advertisement, right? So regression equation can solve my first part. But if I have to answer the second question, like how much should I spend on expenditure? So this is a difficult question, and linear regression cannot answer this question. Why? Because if the beta coefficient is positive, this means that this also says that if you keep on increasing the expenditure on advertisement, it will keep on increasing the impression, which is not the case in reality, because every advertisement has its own life and its own limitations. So after some time, the recall value actually starts going down, and you either have to change the advertisement or you have to improvise the advertisement. So it doesn't make sense to keep on increasing expenditure. There must be something like optimal expenditure which the company must do. So in order to find out anything optimal, you have to use quadratic equation because it gives you turning point. So the beauty of the quadratic equation is that it has a turning point. So it will either have a upper turning point or it will have a lower turning point. So in the cost data, let's say, if you are interested in cost data and try to find out the minimum cost at which the production can be done, so you have to look for the lower turning point of the cost equation. But if you're looking at the advertisement data, then you have to look for the upper turning point. So it depends on the revenue data. You have to look for the upper turning point. So something of this sort. So depending upon what situation you are applying it, if you have to find out the turning point, then which turning point are you looking at? Are you looking at the upper turning point or lower turning point? So here in this case, I'm looking for upper turning point. So that will give me the optimum allocation of expenditure for advertisement purposes. So now the upper turning point, another beauty of the quadratic equation is that it will first give me the rising trend in the upper turning point. It will give me the rising trend, and then it will reach the maximum, and then it will give me the falling trend. So in linear regression, you have either rising or falling. But in quadratic, in the same equation, you have got both the trend. So it first rises and then goes down. So you get the upper turning point. Secondly, it may first go down and then starts rising. So that means it gives you the lower turning point. So that way, it depends on the coefficient, the sign of the coefficient that you are going to get for the second coefficient. So linear equation, the quadratic equation is going to be looking like this one. So if I just give you the idea about the quadratic equation, so the quadratic equation is going to be looking like this one. Y is equal to beta 0 plus beta 1x, beta 2x square, right? So here you have to add this one. So it's a squaring of the x variable. So it gives you the rate of change. This beta becomes the rate of change of the curve. And if the sign is positive, this means it's going to give you the lower turning point. And if the sign turns out to be negative, this means it's going to give you the upper turning point. So this is how this quadratic equation is going to work. So let me estimate the curve and then give you some idea about how it works. So we go to analyze, we go to regression, and this time we are not going to calculate the regression straight away. We go to the curve estimation, let's say. We are going to the curve estimation. So we're going to look at this will also give you the parameters of regression as well as the curve, both. So we go to curve, and it's a beautiful window, which you can see, and the kind of result it will give you is very amazing. So it's asking which is your dependent variable. So dependent variable is impression, because impression depends on expenditure. What is your independent variable is expenditure. So that's the equation that we have formed. Include constant in equation, yes. Plot the model, yes. Which model you want? I want a linear model, of course. I also want a quadratic model. But if you're interested in compound, growth, exponential, cubic, logarithmic, you can just click it and it will give you that model, right? So it's a very important shortcut. And it's a beautiful shortcut, actually. So you just go to OK, you don't have to do anything. That's the beauty of software. And here is the calculations, model summary, everything over here, parameters, everything, and here's the graph. So look at the linear model. So linear model graph is upward going, right? So this means the beta coefficient in linear equation is positive. So if I look at the linear equation here in the table, the R square is 0.425, F is 13 degree of freedom, significance is, P value is 0.001. It's a wonderful model. So the linear equations constant, that is beta 0 value is 22.163 and beta 1 value is 0.630. So my linear equation is y is equal to 22.163 plus 0.6363. So the beta 1 value sign is positive. This means it's going to give me a upward linear curve. So this means it solves my first problem. Does it make sense to spend money on advertisement? Answer is yes, because the beta coefficient is positive and your impression is likely to increase if you spend more. That's one problem is solved. But the second answer cannot be obtained by using this linear equation. and therefore we have gone for quadratic. So if you look at the parameters of quadratic, quadratic is a better fit here. So you look at R square. R square for linear is 0.42, and here for quadratic it is 0.53. So in fact, in this data, the quadratic is a better fit. And the p-value is 0.01, so it's a significant equation. And the constant value is 7.059, and beta 1 value is 1.085, and the beta 2 value, because it has got two betas, the beta 2 value is minus 0.004. As we have already seen that in quadratic equation, if you see it here in the graph, it goes up, goes up, goes up, goes up, and it reaches the maximum over here. And then after that, it starts falling down. So it has got two slopes. So the first slope is actually represented by beta 1, which is 1.085. The rate at which this graph is going up is 1.085. And after reaching the peak, the rate at which it is falling is 0.004. So that's what the graph is all about. And the turning point is here. So those who knows algebra, they will know that the turning point is the place where dy by dx is equal to 0. So here the rate of change in the graph is 0. And if you try to find out the second derivative, d square y by dx square is going to be less than 0. So that means is going to fall after that. So you're going to get the maximum point and the upper turning point in this curve. So now with this equation, how do you calculate? With the graph also, of course, you draw a line and tangent over here. So just draw a tangent over here, and wherever the tangent is going to touch this graph, you just draw the parallel line and make it touch to x-axis. So if x-axis, it is touching x-axis around here, so probably 130, 140. So that is the optimum value of expenditure that you're looking for. But this is a rough estimation because you are measuring it through graph. But can it be also calculated numerically? Answer is yes, it can be calculated numerically. Let's see the numerical calculations, how it comes about. So I'm going to give you the numerical. So here is the numerical calculations. So let me just explain it to you. So we have the quadratic equation. The linear is impression is equal to 22.163 plus 0.363 expenditure. So this is the linear graph. Quadratic is impression is equal to 7.059 plus 1.085 expenditure minus 0.004 expenditure square. So this is your quadratic equation, right? So what you do is that you calculate the dy by dx, the first derivative, and make it equal to 0. So the first derivative is dimp divided dexp. And those who know the derivative algebra will understand how this is equal to 1.085 minus 0.008 exp. And if you make it equal to 0, you get the, if you solve this equation, that you get the expenditure, which is equal to 1.085 divided 0.008, and which is equal to 135.625, right? So you get the numerical calculations over here. And the answer to the second question is that if you want to spend, if you want to keep budget for expenditure next year for advertisement, don't keep more than 135, because 135 is the maximum looking at the market. It is the optimum looking at the market. So any expenditure that you're going to make of beyond 135 is going to be a wastage, because it's not going to add to the impression, or it's not going to add to the sale, for example. So this is going to help you in budgeting and planning for the next year, and also to understand the market very well. So that's how a thinking manager will start functioning. And as a teacher, if you really want to work on these kind of issues and take the expenditure and advertisement and try and see what is the link between the two, explain the market, you can very well use quadratic equation and do it. So is that clear to all of you, or should I explain a little more on this aspect? So any of you would like to ask some questions on quadratic equation? Then I'll move on to the explaining you the logarithmic.
Sir, is there any way to get the exact value in
Any
SPSS directly 135?
No, directly 135 you can't
That
get.
optimal value? Okay.
No. There is no optimization software here. Optimum they will not give you. Graph, of course, you can look at the graph and make it out. It will give you the regression equation. So what I have used is regression equation. So further calculation you have to do yourself.
Oh.
Yeah, okay. Fine. So let's move to a little more interesting application, which is called the logarithmic, right? So I'm going to go to this page and try and understand this. I'm trying to look at the double log formulations. So here, the equation that we are talking about is the functional relationship that we are talking about. The impression actually depends on expenditure. So impression is a function of expenditure. And here we are taking the non-linear formulation between the two, which is impression is equal to beta 0, expenditure is to the power minus beta 1. So if you look at this expression, this expression is actually the non-linear formulation. So what we are going to do is that we are taking log on both sides and get it converted into double log linear function. So if you take log on both sides, so log impression is equal to beta 0 minus beta 1. Log expenditure is the formulation that we have. So this is the formulation. Now we also need to understand a little bit on the significance of this formulation. Why this formulation and what is the application of this formulation? There is something also called the responsiveness of one variable with respect to the other variable. That means we are interested in knowing if one variable changes, what is the degree of responsiveness of the other variable because of the change in one variable. That we are, say for example, in demand, price conditions, we are interested in knowing if the price changes by 10%, then by what percentage the demand is going to change. And this is going to give us a lot of important basis for projecting the demand. Here in this case, let's say if you are interested in understanding if the expenditure changes by 10%, by what percentage the impression is going to change, will give us a kind of elasticity of impression with respect to expenditure, advertisement expenditure. And we can also call it advertisement elasticity, right? So, elasticity concept is very important concept in finance and economics, and it actually gives you a very important basis for projection. So one of the way to project in terms of percentage changes which is likely to be there in the next year or next 2 years or 3 years is to use the elasticity. Elasticity calculation, it becomes easier if you use double log, because double log equation has the properties that the beta coefficient of the double log, the beta coefficient of the double log itself is called the elasticity, right? So no, there is no separate calculation of elasticity you have to do if you're using double log formulation. But if you want to calculate elasticity separately by using, let's say, linear regression, can you calculate elasticity? Yes, you can calculate elasticity. But there the slope or the beta coefficient is not equal to elasticity. So elasticity formula is like a slope multiplied by the point on any curve. That is the concept of elasticity. So you have the slope from the linear equation, but you also have to add point and then calculate manually. Then only you can calculate elasticity. But in double log, the beauty of double log is that the elasticity, that the slope of the curve is actually the same everywhere on the curve. The elasticity remains the same at everywhere on the curve. So in linear equation, if you change the point, the elasticity changes. So if you are in the upper segment of the curve, the elasticity will be different. If you are in the lower segment of the curve, the elasticity is going to be different. But in double log formulation, you be in the upper segment of the curve or you be in the lower segment of the curve, the elasticity will remain the same. And therefore, and this is because of the special property of the double log, because the beta coefficient itself is an elasticity in the double log. So you don't have to calculate elasticity separately. So in order to prove you this point, so I have done this calculation. I don't know how much you will understand, but again, a bit of mathematics is required. But if you're not able to understand, just look at the final result, which I'm going to describe. So here, the concept of elasticity, let's say eta is representing elasticity. Elasticity is equal to, let's say, first derivative of IMP with respect to exp. So this means we are talking about dy by dx here, the first derivative of the equation, multiplied by the point. That means the ratio of expenditure with the IMP on a given point. So that if you multiply the slope with the point, it gives you the elasticity. So if you have to take the derivative of this, I'm just replacing the equation IMP with the formulation which I gave you here, beta 0 exp is to the power minus beta 1. So non-linear formulation. So beta 0 exp is to the power minus b1. So I have just supplemented it in place of IMP. In the next step, the first derivative of this has been obtained, which is going to be minus beta 1 beta 0 exp is equal to minus beta 1 minus 1. So this is going to be the first derivative of this IMP. After that, the exp is multiplied over here, so it becomes minus beta 1 minus 1 minus 1. So plus 1. So plus 1, there is a mistake over here, minus 1 and plus 1. So plus 1 and minus 1 are cancelled, and then what you are left with is in the last step, minus beta 1 is equal to beta 0 is to the power x to the power minus beta 1 you're left with. And therefore minus beta 1 is equal to again exp beta 0 exp minus x to the power minus beta 1 is equal to IMP, because here you can see here beta 0 exp minus beta 1 is equal to IMP. So this whole thing is substituted with IMP over here. So IMP upon IMP you get over here. So these two gets cancelled, and then you get what you get is a minus beta 1. So elasticity will always be in the minus range. So you take the modulus and interpret the elasticity in absolute form. So if you do that, then your elasticity, that is where we started with elasticity calculation with this equation, is equal to beta 1. And beta 1 is what? Beta 1 is the slope of this curve. And therefore, it's very interesting to see this proof of the fact that beta 1, that is the slope of the curve, itself actually becomes elasticity. So it gives you, when I calculate this double log formulation with this equation, you get something like log IMP is equal to 1.300 plus 0.613 log exp. So that means 0.613 is the elasticity. And then this also means that impression is going to change by 61%. Or if the expenditure is going to increase by 10%, the impression is likely to change by 6% for any researcher. And you can actually explain a variety of things using this. So I'll just give you the calculation. So you have to go to the regression and go to, let's say, maybe you can go to the curve estimation as well, or maybe you can calculate it from directly from there, or go to linear. So no, you have to convert that into, if you go to linear, then you have to convert these two variables to convert that. So go to compute, and then we say, I'm trying to calculate log IMP. So this is, give me log IMP. So you take the log functions from here. So there are a lot of functions here. So you click the all functions, and then try and search the log over here. So there are many types of logs given over here, the log 10 base, log natural. So what we are going to use is log natural. So here the description of the log natural is given over here. The numeric returns the base E logarithm of the numeric expressions, which must be numeric and the greater than 0. So you can understand this is for the base 10, and this is for E value 2.17 or something. I don't remember exactly, but it is calculated on the basis of E base. So it's a natural log. It's called natural log. So you click this button, so it goes up over there. Log of what? So I said, okay, log. Give me the natural log of IMP, and then do OK. So the moment I do OK, the log IMP is calculated over here. You can see it's already converted. One variable is already converted. So likewise, I'm going to convert another variable. So let's say in place of IMP, I'm going to put EXP, right? And let's say, okay, the variable name should be log EXP. Then say OK. So I get these two variables converted already in the log. And then I go to analyze, go to regression, linear, and then I'm going to use IMP log and EXP log and say, okay, fine. So give me the parameters. So here the parameters are 1.300 and 0.613. So the elasticity is 0.613. So any change in expenditure, 100% change is going to lead to about 61% change in the expenditure in the impression. So that's how the implication of double log functions. Any question on the implication of double log function?
Sir, hello sir, this is Abhijit Kara.
Yeah.
Actually, sir, I have a question for single log. For example, if we transform a variable, for example, it is expenditure. If I transform the variable into log expenditure, but IMP is only the original value.
Yeah.
Then
So
what will be the?
Yeah, got your points. That's called the semi-log function. This one is called the double log because double log has the property that is beta gets becomes the elasticity, but semi-log function it is not. So what you're talking about is a semi-log. So you're actually converting the independent variable into log, and the dependent variable you're not converting into log. The interpretation of the relationship between the independent and dependent will change in semi-log and the double log. In double log, it has to be interpreted completely in terms of percentage, right? But in semi-log, your the expenditure is in the form of log and the dependent variable is in the form of original. So the interpretation will be different. In simple regression equation, plain regression equation where you have the original variable on both sides, the interpretation is in terms of absolute change. Say, for example, if the beta value is 2, in a simple regression, then your interpretation is that if x changes by 1, the y is going to change by 2. So it's the absolute value interpretation, right? In double log, it is percentage interpretation. So 61%, or if the changes by 100%, then it's going to change by 61%. But in semi-log, the interpretation has to be very different. So I'm not able to recall the interpretation as of now, but what I guess is that you have to convert the beta into the log value
Anti-log,
of the beta into,
anti-log.
again, you have to bring it back by using anti-log. Yeah, so you have to use the anti-log and bring it back and then interpret. So something of this sort.
Okay. Sometimes if there is a negative value in my raw data, so then conversion of logarithm will not work because it will not give any sense.
Yeah, okay.
Then
so,
what I'll do,
you have
sir,
to
in that
see
case?
yes, so you have to see the suitability. So either you can remove, if there are only few, then you can remove those observations and then run the regression.
Sir, Pankaj sir.
Okay.
Yes, madam.
So what I understand is we may have to need, there may be a need to convert one variable into logarithm if both variables are not comparable, like if one is in just rupees and the other is in lakhs of rupees, maybe we may have to convert that lakhs into logarithm so that it becomes relatively comparable. And then finally find the anti-log once you get the regression equation. Is that the
Agreed.
correct
Agreed.
understanding, sir?
Yeah, agreed. It's a correct understanding. So if suppose you have 3-4 variables which are in different measurement expressions, like you have variable is, let's say, distance, kilometer. So you have a very different measurement scale of all the variables, 3-4 variables that you are using. So what to do in this case? If you run the simple regression, again, there is going to be an interpretation problem, the relationship problem, and you'll have to be very careful in interpretation. So when you do the jet transformation of such variables, then they actually become comparable. So after doing the jet transformation, it doesn't make any it doesn't differentiate, or you don't have to look at this sort. So that's why the transformations actually help us in many ways. But what you have said, converting while using the log and the conversion in the same unit is very important. Yeah. Any further question?
Yes, sir. Sir, how
All
we
right.
can,
So, yeah.
sir, how we can decide whether we should go for the reciprocal jet transformation or
Go ahead. Functional form. So every functional form has got its own property, right? It depends on two things. One, what is the objective of the data interpretation or the modeling that you want to do? What is the objective? What is that you want to know from it? What is that you intend to do out of it? So that purpose is one factor on the basis of which you can select. Second is the kind of variable that you have, the type of variable that you have. Say, for example, if I have to project the consumption of, let's say, milk. So my purpose is that my commodity is milk. I want to see what is going to be the consumption in the next 5 years. So I will go safely for double log because of choice by the customer about the milk. So there is not going to be much variation in the choice for milk. That means the consumption pattern of milk is not going to change so much. So I'm safe in my projection for the next 3 years or 2 years down the line, because this is not going to violate, it's not a novel item. But if I have to project for any, let's say, FMCG product, then double log may not be very suitable. I will have to look at also the period for which I'm going to. So I will not go for more than 2 years projection, because the farther the projection I'm going to take, the larger the risk I'm going to carry. Then if you go for another formulations like quadratic, let's say, so if my purpose is to find out the turning point in projection, then quadratic is very suitable. Should I also go for cubic or probably some other? So yes, we can, but depending. For example, if I'm talking about a figure like fish production in a pond, or probably population projections, something of this sort, where the biological multiplications are involved, then cubic is going to be a better projection. Then semi-log formulation. If I'm sure that the projection is going to shoot in one direction, then semi-log is very suitable. So it is actually the nature of the curve you have to study. What is the nature of semi-log curve? What is the nature of double log, cubic, S function? So what are the nature of these? And given the nature of these curves, whether it is suitable to the purpose and the context in which I'm going to apply it. So it has to be a well thought of thing. But statistically, is it possible to select a curve? So most often, for example, in my research, when I was doing my PhD, I did PhD on consumption pattern in urban India. So I took a set of almost like 50 commodities consumed by urban people, and including their personal expenditure on their personal health, hygiene, travel, movie, food, non-food. So, wide range of 50 commodities I have taken. So what I did was that I actually estimated all curves. So including linear, quadratic, semi-log, double log, cubic, all the curves I have estimated for all the commodities. And then I looked at the fitness, goodness of fit for all these curves. And I found that different commodities have a different fit, goodness of fit. So the best suitable curve was identified for each commodity based on statistical criteria. And then I said, okay, for milk, this is fine. For travel, this is fine, something of this sort. So this is one way to do it, but it was a PhD work, so I could do it, but it will take a long time if you do adopt this kind of approach for writing a such paper. All right. So we are left with how much time for this session, Dr. Deepti? 15 minutes?
Yes, sir. 15 to 20 minutes. Yes.
15 to 20 minutes. So let me go to analyze. First, let me seek the data first. Open data. So let me open another set of data. So I'm going to now deal with the car sale market. I said open. So here is a massive data you can see of car sales. So here is the car manufacturers, a lot of car manufacturers you can see here. And this is the model of cars that they are manufacturing. This is the data for the sale. This is the resale value. This is the type of the car, price of the car. And these are the categorical data like engine size, horsepower, wheelbase, width, length, curb weight, fuel capacity. Let me just see because I'm not able to see this part. So yeah, so MPG, that is the fuel efficiency. And this is the in sale means the natural log. The data is converted into natural log because this data set has got lots of issues. So it's one of the best case for converting into log. Anyway, so I'm not coming into that, but if I have to model this car market and try to see what determines the sale of this car. So I go to analyze, then I go to linear. So first I start with the linear and then say, okay, sales, where is the sales data? Sales in 1,000. And then I said, okay, fine. So right from the price, engine, horsepower, wheelbase, width, length, curve, fuel capacity, fuel efficiency. So I have selected all these variables. So how many? 3, 6, and 8. 8 variables. And I'm saying, okay, all of them are independent variables, right? Because the choice of the car or the purchase of the car will depend upon a range of factors, right? And I said, okay, run the linear equation. I said, okay. So get me the result. So here you see the model summary, R is 0.56, that is, and then the R square is 0.3 and the adjusted R square, 0.27, very poor. So, the model is a poor fit because adjusted R square is only 0.27. It's a multiple regression, so I have to consider, I have to look at the adjusted R square. ANOVA table, P is 0.000, that means model is usable. It's not that bad also. That model cannot be used. It's a weak model, but of course it's a usable model, right? Some of the variables must be significant, and that's why the F test is significant. So I'm coming to coefficient. So when I look at the price, how price is significant, the P value of price is 0.547. So can you interpret this 0.547 from your side just to make me assured that you understand P value? Is price significant or not significant? Any response from you?
Not significant.
Not significant. So what is the interpretation of this 0.547? The interpretation of this 0.547 is that if I change this sample of car from the car market, there is 55% chance that I will get a different result. So this means there is very high probability that this result is not valid, right? So it's not authentic. So the coefficient of price is useless for me. I cannot actually use it for any interpretation. So the price is insignificant. Engine size, significant, right? This is what you see. Horsepower, significant. Wheelbase, significant. Width, insignificant. Length, insignificant. Curve weight, 0.03013, significant. And fuel capacity, insignificant. So if I have to go by, if I don't do anything about this regression and go by the result that has been, that is there in front of us, we'll say that the people actually go for bigger and sturdy car. They don't look at price or efficiency for that matter. My conclusion would be that people always go for bigger car and sturdy car. मजबूत होना चाहिए और बड़ा होना चाहिए. Price कुछ भी लग जाए कोई फर्क नहीं पड़ता और उसकी efficiency क्या है हमें मतलब नहीं है. Is it the right conclusion for the Indian market? Not at all. Actually, it is just the opposite conclusion. It is absolutely the opposite, because जब भी हम जाते हैं सबसे पहले mileage पूछते हैं. हमारे लिए efficiency is very important, and at the same time the price is also very important.
It may be feasible only for the higher class.
Higher class, okay. So even in the higher class, there was a paper published. The title of the paper was "Why do you drive BMW anyway?" And this paper was about the people who have actually purchased BMW, and they were asked what was the basic driving factor for BMW. And the conclusion of the paper was that people who purchased BMW was, of course, status is one, but status is not the first or very important factor. Nowadays, people are actually buying BMW because it's more environmental friendly. It's more efficient car. So people are actually paying for environmental protections or environmental concerns. So that's a new trend in consumer. So, you can actually look at all these kind of papers that has been published. There's a lot of paper that can be published in this regard. Anyway, so of course, not the right conclusion. And therefore, what could be the reason? So one of the things that actually happens in multiple regression is that it gives you a kind of, very different kind of scenario, like where your R square can be good and things like that. And then most of the parameters that you are looking for maybe turn out to be insignificant. So why this happens is because one of the assumption of regression is called the assumption of autocorrelation, right? So there is a term called autocorrelation. So regression is also based on the assumption that the independent variables are themselves are not related to with each other. Just to give you an example, if I have to explain consumption, then I'll from theory I will say consumption depends on income. I'll take income as one variable. Then I will say, oh, consumption also depends on wealth, even if your income is higher or lower. But if you have a lot of wealth, you can consume more or less, right? So it also depends on wealth. I will say consumption also depends on assets that you have. So I will take income, wealth, and assets as the explanatory variable.
Sir, sorry to interrupt you. I think you are talking of multicollinearity rather than autocorrelation.
Oh, sorry. You're absolutely right. Multicollinearity. Yeah. Oh, thank you. Who was that?
Myself, Dr. Devi Prasad, sir, from Odisha.
Oh, thank you so much. Yeah, thank you, doctor. Thank you for pointing out. Yes, I'm not talking about autocorrelation.
Yes.
I'm talking about
It
multicollinearity.
just happened.
Autocorrelation is, yeah, we look at autocorrelation in time series.
Yes, sir. It
not,
comes spontaneously because.
Yeah, fine.
Not series.
Thank you.
Thank you
For this correction. So, yeah, so consumption depends on these three factors. So this is what I'm formulating. But when I start looking at the interconnections of these three variables, I found that people who have more, assets or more wealth are also having higher income. So it's a source of income as well. And therefore, income and wealth and assets they themselves are correlated with each other. And therefore, the part of the explanation which is coming from income for consumption is also being accounted for by the asset and the wealth. So the same thing which is explained by income is also being explained by the other variable. So assumption of the very important assumption of OLS is that the independent variables should not actually correlate with each other at all. They should be actually very, very independent, so that the impact of these independent variables are separately felt on the dependent variable. So the part of the explanation that comes from one variable should not be coming from the other variable. So that's the assumption. So if that happens, then it creates this kind of scenario. So it's a clear-cut case of multicollinearity. If you look at the correlations table of all the variables with each other. So in such case, what we do is that we go to, let's say, analyze, we go to linear, the same table, and then what I'm going to do is that I'm going to click this method. So we change the OLS method. So there are many methods like stepwise regression. There are other ways of looking at backward, forward regression. So most popular is the stepwise. So I have clicked the stepwise method. So I change the method from simple regression to stepwise regression. So in a stepwise, the computer is going to build iterations. Based on the iterations, it will build the models. So it will take the first model, all the significant variable together, and then again it will start iterating again, and then leave out the insignificant variable, again build another model. It will keep on actually building on the model 2, 3, 4 models for me, and the last model that is going to build is going to be the final model for me. And the last model is the one where only those variables will appear which have no connections with each other, and they are very independent, and they are significantly affecting the independent variable. So that's how it's going to happen. So let's see the model, how the result actually looks like. So here you can see there are two models that has been created by the computer. So model 1 and model 2. And then you have the model summary of both the models. You have the ANOVA table of both the models, the coefficients of both the models, and what are the variables that has been excluded. There is a list of variables over there. So our concern will be to interpret the last model, which is the second model in this case. So in this case, if you look at the second model, there are two factors that has emerged. One is the wheelbase, which is significant, and the price in 1,000, which is also significant. This means now we have the right conclusion that wheelbase means people are looking for bigger car, and price means people are looking for cheaper car. So the market, result for the market is that it's the bigger and cheaper car which will sell, which is going to sell more, right? So that's what the result is here in this equation. So we go to the chart builder, let's say, just to give a little more insight into this market. So we go to scatter plot again, because scatter plot is a very wonderful tool of understanding the data to derive some wonderful conclusions. So here what we do is that we are going to look at, let's say, fuel efficiency, maybe on one hand, and the car sale on the other. So we want to take this novel factor because fuel efficiency is a very important factor. And we say we also would like to have the cars to be displayed over there, so that we can understand the graph well. So we have this scenario over here. So you can see, so there are two cars which actually have been figured out from this equation, right? From this whole data. Rest of the cars are actually forming a cluster over here. There is one car is called the F series. Another is called car is the Metro. So here in Metro, we find that a Metro is very high on fuel efficiency, very low in price, right? But F series is a very high on price, very high on sale, not price. So F series, Metro is very high on a fuel efficiency, low in sale. But F series is very low on fuel efficiency, but very high on sale. So we have these two kind of extreme examples available in the market, but rest of them are actually clustering around the same thing. So probably these are the two outliers. We call it outliers. So these are the two outliers existing in the model, in my data set. So one thing that we can do with the outlier is to remove them. So remove these two data and then be comfortable and run the regression. So that can be one way. But as a researcher, you may like to look at this model where the sale is very high, even though the car is very less fuel efficient. So if you're a new car manufacturer, this F series is a model to be looked at. What makes this F series actually sell more, even though the fuel efficiency is less? So you can remove Metro, but you would like to keep F series in your model. So if suppose you want to keep F series, what will happen to your model, to your data? It will actually create more variability in the error terms because you have the outlier present in your data. So what you can do is that you can convert this data into log to reduce the variability, because invariably, if you convert the data into log, the variability goes down, right? So that's how it works. So you convert into log, and that's why the sale data is converted into log. And then if you run the regression, you might get a very good, first convert the data into log, the sale data, and then remove Metro from the data. So it will give you a better positioning to deal with this data. It doesn't mean that it will remove all the problems, but there will be some problems still remain, but it will at least give you a better insight into the market if you do that. So time is almost over. I'll stop here. If there is any question, we can discuss that and then meet again after lunch.
Dear participants, if you are having any queries, then please ask, sir. Else we'll resume back in an hour. Is it fine for you, sir? Because we have
1 hour is fine.
1 hour, okay.
1 hour means 2:30. We are back by 2:30.
Yes, we'll be back by 2:30.
That's fine. It's absolutely fine with me.
Okay, sir. I guess participants. Yes. Somebody wants to say something.
How you have analyzed these different models from the SPSS? Can you tell me once again the process?
I didn't get your point. How to analyze?
Because you have analyzed the different models which can be prepared initially before coming to the graph by using the SPSS. So how you got it?
You mean I'm still not able to? You mean this one?
No, actually I am talking about the SPSS result previous to this. Before coming to the graph.
Before coming to the graph. Oh, okay. This one? Yeah. So you want me to repeat it again?
Simply the steps, only the steps, not
steps.
to repeat.
Okay, fine. So go to analyze.
Yeah.
Go to regression.
Okay.
Go to linear. Enter the variables. Go to method. There is something called method over here. You can see I'm moving the cursor. So if you click this window, this drop down menu, you have the different methods over here, forward, backward, stepwise, right? So I just clicked stepwise. But if you keep enter, that means it's a normal regression, simple regression. But if you choose stepwise, it's a stepwise regression. So it will give you the stepwise result.
Yeah, I got
it.
Right.
So
thank you.
Yeah, so you just say okay and you get the result.
Yeah.
So is it possible to get this data file? So during this 1 hour, participants can do some hands-on practice.
You're not going for lunch?
No, they will go for the lunch, but I think in half an hour they can do it some hands-on practicing.
I was just it was on the lighter side. I'll send you all the data. Don't worry.
Thank you
So
very
should I
much.
send it just now?
That would be better, sir, if possible.
Okay.
If
So
it is convenient for you.
Whom should I send?
You can send it on my email ID, so we will forward to all the participants.
Dr. Deepti,
Yes,
you want
sir.
me to send it to him, or should it be sent to you?
Sir, either ways, you can send it to Mitra sir only. No issues.
Okay. So give me the email ID.
Sachin.mittal. I am writing in chat box, sir.
Oh, Sachin ji. Okay. Sorry. Yeah. I after a long time I'm seeing you, so I couldn't see your name over there. Okay. So
No
sorry,
issues.
Sachin ji.
No issues, sir. No issues.
Sachin.
Mittal.
Yeah, your email ID is with me only. Sachin Mittal at yahoo.com.
Mittal @ipsacademy.org.
ipsacademy.org.
Right.
All right away. I'm sending it right away.
Thank you very much, sir. Thank you.
Okay, thank you.
Okay, thank you so much, sir. Yes. So, dear participants, we will be back at 2:30 sharp. Thank you so much, sir. Thank you.